Hello everyone. I am Anuj Kumar. I am the PMRFTA for this course. So, today I will be discussing assignment 9. Okay. So, the assignment 9 is related to the application of crystal field theory and spinels, right? So, as usual, I will show you the two problems and I'll wait for your answer. Thereafter, I will explain the same. Okay. These are the first two problems. In the first one, you have to just calculate the magnetic moment for these two complexes, right? In the Bohr magneton, you are given four options. Just you have to identify the unpaired electrons and put them to the respective formula. Here you have to use the simple formula, that is under root n into n plus 2, right? And the second one, you have to identify which metal ion will have the lowest hydration energy. So 2 minutes, I'll wait. In the first question, you can see there are two complexes. Okay, so in the first one, there are two complexes. First one is having a weak ligand, and in the second one is a strong ligand, other is the weak ligand. Okay, so you just have to identify the electronic configuration and calculate the magnetic moment using the formula and let me know, please. First, determine the oxidation state. In the first one, cobalt is plus 2, and also in the second one, it is also plus 2, right? So it will be having a D7 configuration. Okay. So in the first one, since bromide ligand is a weak ligand, so there will be no pairing. Okay, and both the complexes are octahedral, right? So in the first one, the unpaired electron is 3, but if I talk about the second one, n equal to 1. Okay, so apply the simple formula, that is n into n plus 2. It will be under root 15. Just calculate it. It will be around 3.87, right? And what about the second one? It will be under root 3, that is 1.73. So this will be the right answer. Okay, so here is the explanation. uh, yeah, I have explained earlier. So these are the electronic configurations you will be getting, and accordingly you can get the magnetic moment value. Okay, so the moving to the next, that is related to hydration energy. So just read this explanation. The most common example of crystal field stabilization energy in the thermodynamic aspects comes in the form of exothermic enthalpy of hydration data for the bivalent ions of first transition series. Okay, which usually have six water molecules in the hydrated form. So general reaction is this, right? Now the value of enthalpy of hydration should become increasingly exothermic as we move along the row in the transition series, right? Okay, so some certain configuration which have extra stability in the octahedral hexaecho complex, just like this, right? So it is a D5 complex basically, right? And there are 5d electrons, and so zero crystal field stabilization energy. And we can see that the hydration energy is that predicted on a purely electrostatic basis. Okay, so I will show you the trend, this one. Okay, so using this formula, using this diagram, you can get the elementary idea about the hydration energy of these bivalent cations, which will have the lowest one, right? Okay, right. The second two, there is you have to determine the composition. What is talc? Talc is basically composed of ammonium iron sulfate, potassium aluminum sulfate, hydrous magnesium silicate, or it is potassium sodium tartrate tetrahydrate. Okay, I think it is a hydroxy magnesium silicate. Okay, so first provide me your answers, then I will make you know. And second is about the spinel structure. You have to first you have to identify whether it is a normal spinel or inverse spinel, and from that you can get the elementary idea about this trivalent iron will be occupying which site, tetrahedral or octahedral. Okay, so just try at your own and tell me. Okay, talc is hydrous magnesium sulfate. It is not sulfate actually, it is silicate, right? Okay, what about the second one? Anybody? Okay, so moving to the explanations. So if I talk about the talc, it is a the formula. Okay, so you can see it is a hydrated magnesium silicate basically. Okay, and if I talk about the second one, okay, so here are some details from which you can identify whether this oxide Ab2O4 type oxides are normal spinel or inverse spinel, right? So basically, if I talk about the normal spinel, sorry, so in case of normal spinel, this will occupy tetrahedral voids, okay, and these two occupy octahedral voids, right? But in case of inverse spinel, this will be occupying octahedral, and this B also, one of half of B will occupying octahedral, and another B will be occupying the tetrahedral voids, right? So if if the bivalent cation is having a higher crystal field stabilization energy in an octahedral field compared to the trivalent ion, you will be getting a inverse spinel, right? Or if a trivalent ion has a higher crystal field stabilization energy in an octahedral field compared to the bivalent one, it will result a normal spinel. Okay, so if I talk about this complex, that is COFe2O4, you can see Fe is in plus 3 oxidation state. It is having a D5 configuration. Okay, so D5 configuration will be showing no crystal field stabilization energy. Okay, whether it is in octahedral or tetrahedral environment, it will be having no crystal field stabilization energy. But if I talk about this cobalt 2 plus, that is D7 configuration, as compared to this D5, it will be having some amount of crystal field stabilization energy. Okay, or if you want to calculate, okay, just put it is D7, okay, and fill the electrons in T2Z and easy level, considering this oxygen as a weak ligand. Okay, so here Fe plus 3 is having a low stabilization energy as compared to this cobalt plus 2, right? So this oxide will exhibit the inverse spinel structure. Okay, so the answer of first one will be this one. Okay, yeah, so it is asking about which uh, site it will occupy. So as I have explained earlier, in inverse spinal, Fe plus 3 will be occupying both the octahedral and tetrahedral sites, right? So the answer will be this one. Okay, so moving to the next two, here are other examples. You have to identify which is the normal spinal structure. Okay, and the next one is related to the longest octahedral crystal ionic radii. Okay, so if you know the answer, please tell me. I will wait for 2 minutes and thereafter I will explain. Any guess? Just identify the metal ion and its electronic configuration. Just basic calculate the stabilization energy, and if the bivalent ion is having more energy than the trivalent one, it will be a inverse spinel, or it is opposite, then it will exhibit the normal spinel structure. Okay, and apart from that there is also a technique. Yeah, so I got hmm, yeah, so there is you can basically calculate. So if you don't know or you have no any elementary idea about uh, whether it will be exhibiting normal spinel or the inverse spinel structure, what you have to do basically, just put the conditions of both the structures. First, consider the this oxide as a normal spinel. Okay, and you know already that in normal spinel, one the bivalent cation is in tetrahedral complex. So considering this environment, calculate its crystal field stabilization energy, right? And calculate the same for b plus 3. Okay, yeah. So after that, there are two b. Just multiply that value by 2 and add both the values. Okay. So you will be getting a total value in case of this oxide is having a normal structure, right? In second way, consider it as a inverse spinel, right? And calculate the crystal field stabilization energy accordingly. Yeah. So what you have to do basically, I'm saying you are adding these values. So delta T and delta naught cannot be added. Okay. So what you have to do, you have to convert that value, that is tetrahedral crystal field stabilization energy, to octahedral. So delta T equal to 4 by 9 delta no. 4 by 9 delta octahedral. So just put that value in place of delta T, you will be getting the value in terms of octahedral from crystal field stabilization energy. And you after that you can get the total energy only in terms of delta O. Okay. So now you are having two values. One is for normal spinel and second is for inverse spinel. So just compare the energy values, and more the value you will be getting, the more structure, the more will be the stability of structure. Okay, so you can just determine whether it will be a normal spinal or inverse spinal accordingly, right? Yeah. So tell me, what will be the answer? I think someone has already given. Yeah, please once explain calculation of crystal field stabilization energy. Okay, so right, so I'm considering the Mn3O4. Okay, my pen is not working properly. So Mn3O4. Okay, so you can write Mn2O4. Okay, so it is having plus 2 and it is having plus 3. Okay, so the electronic configuration for this will be, what it will be, it will be d5, and for this one it will be d4, right? So just considering it in a tetrahedral environment. Okay. So what will be the electronic configuration? It will be EZ 2 and T2Z 3. Sorry, not G, just E. Okay. And if I talk about D4 in octahedral, so what will be the electronic configuration? It will be T2G3 and EZ1. Okay. So in tetrahedral complexes, when there is a splitting, okay, this is EZ and this is T2Z. So I am filling the electrons basically, and this is Berry center. Okay, and this is zero point 0.6 delta T, and the upper one is zero point 0.4 delta T. Okay, so just multiply 3 multiply by zero point 0.4, that is 1.2 delta T, and minus 2 multiplied by zero point 0.6 delta T. So 1.2 delta minus 1.2 delta, that will be 0, right? In the same way, you can calculate for the octahedral complex. Understood? If you got my point, please type yes. What you have to do? Yeah, thank you. Okay, just consider them as a complex, and according to the metal and its oxidation state, just fill them in the respective orbitals, and you will be getting the crystal field stabilization energy. Simple. Okay. So moving to the explanations. So this NiFe2O4 is an inverse spinel. You can just do the basic things. Okay, whether Fe the bivalent cation is having more energy than +3 in octahedral, or +3 trivalent cation is having more energy than +2 in octahedral. Okay, from that you can get the basic idea whether it will be an inverse spinel or normal spinel structure. Okay, so if I compare both the metals, right? So in D5 there will be no crystal field stabilization energy, but it compared to this, a D8 ion will be having more crystal field stabilization energy. So hence the former ion will preferentially occupy octahedral voids, right? And Mn3O4 is a normal spinel. Since the manganese plus 2 ions is a high spin D5 system with 0 LFSE, as I have already explained that it is having a 0 ligand field stabilization energy. Okay. So if it is a normal spinel, it will occupy the tetrahedral voids. And Mn plus 3 is a high spin D4 system with considerable low field stabilization energy. So we'll occupy the octahedral voids, right? So Mn3O4 is a normal spinel structure, right? And the other three are the inverse spinel. Okay. The next, yeah. So among the following, the metal ion with the longest octahedral crystalline radii. Okay. So in case of vanadium plus 2, right? Yeah. So vanadium plus 2 will be 3D 3. Okay, yeah, 3D 3, and it occupy only T2Z. But for as the easy orbitals point directly towards the ligand, the repulsion between the metal electrons and the ligand electrons will be higher than normal, leading to the eventual increase in the ionic radius. Okay, for Mn plus 2, that is d5 high spin, you have to consider high spin in this case. Okay, yeah. So number of electron further increases, hence ionic radius will be further increase. Okay, so basically this question is related to the inter-electronic repulsion that is being held between the metal atom and the ligand, right? So, easy orbitals are along the axis orbital, right? And T2Z in between the axis. And in octahedral complexes, the ligand approach towards the metal through the axis. Okay, so if there is electron in the easy orbital, that will be causing the repulsion, that will be generating the repulsion to the ligand. Okay, so in case of manganese plus 2, number of electrons are increasing, or the easy orbital is having electrons, so that will be having a high ionic radius because of this electronic repulsion, right? So the next two, the divalent metal ions occupies only tetrahedral sites in case of inverse spinel, normal spinel, neither normal or nor inverse, or both normal and inverse spinel. I think I have already discussed these things. Okay, so just tell me the answers. Yeah, so Mn plus 2 D5 octahedral crystal field stabilization is 0, and D4 Mn plus 3, there is CFSE. Okay, so higher CFSE for plus 3 ion, so it occupy octahedral sites. Okay, so just if you have already calculated the CFSE value, then just you can provide me the values, please. So calculate the value for D4. Have you calculated? Yeah, zero point 0.6. Okay. So in case of normal spinel, so divalent cation should have a lower stabilization energy, right? And in case of normal spinel, Mn plus 3 should have larger value, right? So D4 electronic configuration is having higher value, so it will be normal spinel. Then what is the problem? I could not understand. In normal spinel, the plus 3 cation should be occupying octahedral voids. That is right, because it is having a normal spinel structures. I think I explained the same, right? So Mn plus 3 is having higher CFSE, due to which it will tend to occupy octahedral sites, and Mn plus 2 will remain in the tetrahedral field, because in case of tetrahedral field also D5 is also having a zero stabilization energy. Okay, are you getting my point? If yes, since in plus 3 oxidation state, Mn plus 3 is having a higher crystal field stabilization energy in octahedral field than Mn plus 2. It will be having a normal spinel structure. Okay, so that was the question asking about. Okay, so moving to the next one, that is the divalent metal ions occupies only tetrahedral sites in case of, okay, so AB2O4 plus 2, a bivalent cation will occupy tetrahedral sites in case of normal spinel, right? And the metal ion present in lignite. Okay, so here is the explanation. In case of normal spinel, the divalent ions occupy tetrahedral voids, whereas the trivalent occupies the octahedral voids. So thus a normal spinel can be presented as this one. Sorry, like this. And in case of inverse spinel, the bivalent ions occupy octahedral voids, as well as this half of one half of trivalent cations occupy tetrahedral voids, right? So it can be represented as this one. Okay, you can see A in plus 2 oxidation state and B in plus 3 oxidation state in octahedral environment. But in normal spinel structure, the bivalent cation is in tetrahedral environment. Okay, so this will be the right answer. Okay, and the metal ion present in linearite. It is a basically thiospinel with the composition of this cobalt metal in plus 2 and plus 3 oxidation state. Okay, so it was discovered in 1845 in Sweden. Okay, by this man Carl Linus in Wasmanland. Okay, so it is having cobalt plus 2 and cobalt plus 3. Okay, so the next question is related to ruby. You, I think already sir have discussed twice about this ruby, the doping. Okay, so corundum is alumina, basically Al2O3. Okay, just tell me which metal ion is doped into this. Okay, very simple question it is. Yes, chromium, no problem, sir. Normal spinel calculation is easy, but tetrahedral field we have to consider both cases. Yeah, yeah, you can consider both the cases and compare the energy values. That procedure basically consumes the time, right? as I have already indicated, that first assume any oxide, it is having a normal spinel structure, and calculate the energy accordingly. And in the second part, consider it as a inverse spinel. Okay, but for comparing the value, you should have the energy value in terms of either in it is in tetrahedral crystal field stabilization energy terms, or it is in octahedral crystal field stabilization energy terms. So you can just interconvert the delta t to delta o. Okay, if you are having a value of delta t is 3, right, multiply it by 4 by 9 delta o, so you will be getting 4 by 3 delta naught in case of octahedral complex. So the comparison will be easy for you, right? Without converting to the common term, you cannot compare both the values with each other, right? Okay. So the artificial ruby is often made by simple doping a trace of chromium in artificial corundum, that is aluminum oxide crystals, right? So the resulting crystal has the same internal atomic structure as natural ruby, as well as the same optical properties, hardness, and chemical composition. Okay. So the chromium plus 3 will be the right answer. Okay. So match the following. Here are some composition names, and you have to identify the respective formula: polydimite, indite, and carolite. Okay. So these are the formula and names you have to remember. All are thiospinels. Okay. So if anybody have remembered, please tell me the answer. Indite, as its name indicates, it contains indium, right? So the answer for second will be Y, right? Okay. So here is the explanation. Indite is an extremely rare indium iron thiospinel. Its chemical formula is this one. And polydimite, that is Ni3S4, is a supergene thiospinel sulfide material. And carolite, it is a mix of metals, that is copper and cobalt. All are thiospinels. Okay. So the carolite will be this one, indite will be this one, and polydimite will be this one. So X, Y, and Z. This sequence will be the right. Okay. So the next, along the 3D series, the heat of hydration are consistent with the expected crystal field stabilization energy for the metal ions, and so two humps, a straight line, one hump, or three humps. In this class, I have already shown the diagram like this one. This is manganese. Okay. So you will be getting two humps, right? Let me show you the diagrams. This one. Okay. and the correct spinal structure of CO3O4. Okay. So first you have to determine whether it is a normal spinal or inverse spinal, and if you have that information, you can easily choose the right option. Okay. So tell me, this CO3O4, it is a inverse spinal structure or normal spinal? Anybody? First A and second B. Okay. Yeah, right. Since it is having a normal inverse spinal structure, okay, so it will be having this composition. One trivalent cation is in tetrahedral void, and one plus 2 and 1 plus 3 each occupying octahedral voids, since it is a inverse spinal structure. Okay. So this is a complex. You have to calculate the spin only and spin orbit magnetic moment value for this complex. And in the second one, yeah, the same thing. The spin, since likely to have a normal spinal structure, because you have to basically tell me the reason why it is likely to have a normal spinal structure, because the plus 3 cation will have energy, more energy as compared to plus 2. Okay. So I have already given you the answer. Just tell me the right option for both these. Okay. In the first one, that is chromium plus 3, that is 3D3. Okay. Since it is an octahedral environment, fill the electrons, it will occupy only the T to Z levels. Okay. Hence, all the electrons will be unpaired. So a spin value will be under root 3 multiplied by 3 plus 2. That is under root 15. Am I right? So it will be having most likely 3.87. Okay. And for the spin orbit coupling, you have to apply this formula. That is 4s s plus 1 plus l in l plus 1. Okay. So s value you have, you already have. Okay. And l value you can calculate 1, 2, and 3 plus 2 plus 1 0. So it will be having L value 2 plus 1, that is 3. Okay. And what is your spin value? That is 3 by 2, because all the 3 electrons are unpaired. So just put this value in this formula, and you will be getting the value of spin orbit coupled magnetic moment. Okay. Just calculate and tell me what value you are getting. Anybody? Yeah. First B and second B. Okay. But I think the B is the right statement, but it basically not explain. It is not explaining why it is having a normal spinal structure. Okay, so the structure is decided on the basis of LFSE values only. So basically, you have to identify the bivalent cation or trivalent cation, which one is having a higher LFSE. Okay, so in the first one, you are getting this value, that is 5.20. Okay, you can calculate easily. Okay, and in the second one, this will be the right answer as I have explained it many times. Okay, among the compounds, just identify the normal spinels and inverse spinels. Okay, follow the same procedure and you will be getting the answer. Okay, yeah. The next important question is the magnetic moment of this ruthenium complex correspond to the presence of, you have to identify the unpaired electron in this one. It belongs to iron group. Okay, and what is the electronic configuration? Since it is in plus 2 oxidation state, it will be having 46. Okay, so it is a transition metal of 40 series. Okay, so it is a very interesting question. Please tell me the answer if you know. It is having how many unpaired electrons? Second is A, 4 unpaired electrons. Okay, you know, only the 3D transition series is having both high spin and low spin complex. If you move from 3D to 4D, right? So 4D transition series exhibit the low spin complexes, even with weak ligands also. Okay, so the water here will behave as a strong ligand and will pair up the electrons, right? So this complex will be having zero unpaired electron because it is a 4D transition series metal atom. Okay, the trend of this energy gap. Okay, sorry, the energy gap follows this order. Okay, so as compared to this 3D, the electronic energy gap, stabilization energy gap, that is this one, is very high for 4D and much much higher for 5D. So if this delta O is very very high as compared to pairing energy, so these electrons will be paired up and will show a diamagnetic behavior. Okay, yeah. So the last two questions. These two oxides are metal oxides having a spinel structure. Considering their CFSE, the correct statement regarding their structure is, okay. I think CO3O4, as have I have already discussed, that is, I think it is having a inverse spinel structure. And what about Fe3O4? Just practice. Okay, put the bivalent and trivalent cation in the octahedral as well as tetrahedral or environment, calculate their CFSE and compare, and you will be getting the right answer. Okay, you can try also. So the next one is arrange the following metal complexes in the order of their increasing hydration energy. Okay, just keep that diagram in your mind and compare the hydration energy. Okay, let me see, is anybody providing the answer? Okay, first T and second A. Okay, yeah. So this is the diagram, right? So if I draw the hydration energy, that is nickel plus 2. Nickel plus 2 is having a hydration energy of corresponding to this value, right? And what about manganese, vanadium, and titanium? Okay, so manganese is having the value of something like here, and vanadium is here, and this titanium is here. Okay, so the higher value you are getting in case of this complex, that is nickel complex, right? So this will be having a higher value. So which option will be right one? This R. The first option is because R is having a highest hydrogen energy. Okay, so this was all about this session, today's session. Thank you very much for attending. Okay, I will just recommend you just practice these normal and inverse spinel structures, calculate the CFSE values. Yeah, can you explain second question? I think I have explained earlier. So you can see this figure, and you see the nickel plus 2 is having highest hydrogen energy. Okay, number first slide. Okay, okay, okay. So I am going there. I think book suggestion. Okay, yeah. First, I have to go first slide. That is plus 3. Okay. So the metal ion with lowest hydration energy is. Okay. So here is the explanation. Just read it and tell me where is the confusion. Am I audible? Okay. So, yeah. So the metal ion with lowest hydration energy, right? You know, the hydration energy is reversely proportional to the size of ion, right? Okay. So if you compare the 3D series, okay, among these, which will be having the lowest size, or you can say the highest electronic radii. Okay, so the most yeah, the value of enthalpy, since it is a exothermic reaction, the hydration energy. Okay, so the enthalpy of hydration should become increasingly exothermic as we move along the row in the transition series, right? The spherically symmetric ions increase their nuclear charge, which further enhances their attraction for the incoming ligand. Okay, what I'm trying to say, uh, yeah. So if I'm having Fe plus 2 and Fe plus 3, so which will show the greater interaction with ligand, plus 2 or plus 3? Obviously plus 3, right? Yeah. So the discrepancies, yeah, so nuclear charge increases their attraction for the incoming ligand, but the discrepancies obtained in the experimental and observed value can be attributed to crystal field stabilization energy values, since the difference between two values is roughly equal to the CFSE values determined for high spin complex. Okay, the symmetry of ion changes from spherical in the free ion to octahedral in the complex. Okay, so the splitting of energy of d orbital takes place. Okay, so what I am talking about, okay, sorry. So it is a free ion that is spherical. Okay, and when the ligand approach, the splitting is there and it is exhibiting the octahedral environment. Okay, so the splitting of energies of the orbital take place, the number of electrons then determine the total crystal field stabilization energy. Hence certain configuration have extra stability in this complex. Okay, so here the hydration energy is basically predicted only basis of electrostatic attraction. Okay, so due to which it will, the iron plus 3 will exhibit lowest hydration energy. Okay, so if you know, if you need more explanation, I will just post it with the question to the discussion forum. Okay, yeah, from there you can get the whole details, whether how this spherical ion is transiting from a spherical to octahedral, and how, when, in which particular case the hydration energy is predicted only on the basis of electrostatic attraction, and how it depends upon the number of electrons. I will just post. Okay, and from that you will be getting a more clear value, right? Yeah, so thank you very much for attending this session. If you have any problem other than this, just post simply to the discussion forum, and I'm there to answer the queries. Thank you. Thank you very much.